Continuing from the last recording. So we want to measure the phi now one more time. So let's do it. The alpha carbon 2, 3 and 4. You can see this is right now is minus 169 degree. So that falls within this range, that is within minus 120 to 180 degree for phi. Okay, so that we should be in this. So let's measure the energy for this system. So if you go to molecular mechanics, calculate energy. So this is showing 252 kilojoule per mole. Okay, so let's write that down. Okay, so we should just double check the other energy also. Okay, so that would be that should be starting from here. That is from the C-terminal alpha carbons amino acid. C-terminal alpha carbons alpha amino should be the 1. So 1, 2, 3, 4. So 165 degree. So that is the psi. That is 165 degrees. So we are well within this range. So we got the energy for this one. That is plus 252 degree. Okay, so that is the energy has a measure of plus 252 degree. Okay, so let's try the next one. So we'll keep the psi unchanged because they have similar number, and we'll keep it at close to 120, and we'll keep change the phi to plus 120 to 180 degrees. So let's keep it at 150. If we look at it, so psi 120 is somewhere here. Okay, psi 120 is somewhere here, and phi 150 is would be somewhere here. Okay, so this is the position we should look at. So let's put a little box right there to make it understand you guys. So this is somewhat what we are talking about. Okay, so this is plus 120 and plus 150. So that is the position what we are referring to. Let's see what energy we get that. So theoretically that should have a higher energy than this one, because that should have a higher steady clash. Okay, so we are keeping the psi to be 120. So let's bring it to 120. How do we do it? So we go to this angle change, on angle rotation, and it is still 165. So we rotate it and decrease it to 120. Okay, so this you can see I have decreased it to 120. Okay, so the psi is now 120. The next thing we want to do, we want to change the phi to be 150. Okay, so plus 150. So that should be right here. Okay, so let's do it. So this is starts with this carbon 1, 2, 3, 4. So plus 150. So right now it is minus. So if you can do it, this is the bond we want to rotate for the phi to change. So let's increase it. So we want it to be plus 150. Crossed it. There we are. Okay, that is plus 157. That is fine. So now let's measure the energy for this. Okay, so you can see that has increased, right? 324. So the energy has become plus 324. Okay, so meaning that that position is less stable. Okay, so that position is less stable. So if we look at this, why that would be? Because you can see that these two hydrogens are almost facing each other. So which is why there is a steric clash. Okay, so that is why that position probably is unstable. Okay, so that position we can say that is higher, so that should be unstable. Now let's try this at minus 60 plus and minus 60 for phi and minus 60 for psi. So minus 60 for psi is right here, and minus 60 for phi is right here. So that should give us somewhat stabilization. So this is the area we are talking about. So minus 60 for phi, minus 60 for psi. Okay, so let's change it. So right now we have the phi selected already. So let's rotate it to bring it to minus 60. So okay, minus 60, right? So that is right here. Now if we try to do that for the other one, for the psi, so let's try that. So that numbering should start from, we can see for the side, the numbering start from the nitrogen on the next carbon, that is right here, 1, 2, 3 and 4. Okay, and we should rotate this angle for the side to change. Okay, so that we should bring it to minus 60, right? So minus 60. Let's rotate this. Okay, so that is minus 60. So let's try this to see what angle this is, or what energy this is. So this is 313,199. Okay, so 313,199. So that is 313. Okay, so that is this region. So again, the energy is slightly less than this. So we are seeing some structures right here. Okay, we are seeing some structures right here. So 324 became not so stable, but 313 is slightly stable. So we are seeing some structures right here. Okay, so that is that. Now let's try the next position, that is next quadrant. So again, what we are going to try is we want to try the phi to be 0 to minus 120. So we can try this position right here. That is, we can try the phi to be, let's say, 60 degree or minus 60 degree. Okay, so phi to be minus 60 degree and psi to be minus 120 degree. Okay, so we should have a theoretically higher energy than this one even, because this is not supposed to be very stable, right? So let's increase the phi, but let's see what we already have right here now. So we already have the psi angle, dihedral angle selected. So let's increase it to psi. Let's increase the psi to 120 degree. Okay, so let's increase the psi to 120 degree. So minus 120. So you can see now it is, the psi is minus 120. Now increase the phi to minus 60 degree. Okay, so let's change it. So numbering should start from here. Okay, so it is already minus 60 degree. Okay, great. So this is already minus, phi is already minus 60 and psi is already minus 120. So let's measure the energy right now. So 343 again, right? So you can see that it has become 343 again. So it is similarly become unstable. Okay, now let's try the other part, that is this quadrant D, where 0 to plus 180 we are visualizing. So that it should be, let's take a number which is 120. Okay, let's take a number of phi, that is 120 plus 120 degrees. So that should be somewhere in here. Okay, so plus 120 degree. Okay, and let's take the psi to be minus 60 degrees. So psi minus 60 is right here. Okay, so psi to be minus 60 is right here, and phi plus 180 is right there. Okay, so that is the position what we are referring to. So let's see what energy we get there. Okay, excuse me. So right now we have chosen this as the phi. So we want the phi to be 120 degrees. So let's change it to plus 120 degree. Plus 120 degree. close to 120, anyway 123 degree. And let's try this on psi to be minus 60. Let's try the psi to be minus 60. So let's try that. Start from here. 1, 2, 3, 4. 120 degree. Sorry, psi to be minus 60 degree. So it is minus 120. So we want this to be minus 60. Other way around. Minus 60. Okay, so you can see this is the position that we got. Okay, let's check out what is the energy for this one. So 373. Right, so this got the highest energy of what we have calculated so far, 373. So you can clearly see that this is also unstable. Okay, so to summarize, what we got here is that we got so this part is the lowest energy, this quadrant, and out of the everything that we measured, and that explains why you have so many types of structure over there. This ones, on the other hand, these are like somewhat unstable. This particular was stable. This is like quadrant C right here, so that gives rise to some of the structures right here. Other than that, these are also mostly unstable. So that's why it explains there are mostly no other structures in this. Okay, so that's how you can qualitatively prove the Ramachandran's diagram. So how does the each amino acid? So this, when we discuss this, see what we just discussed is the interaction between the dihedral plane on this side and dihedral plane on this side. We did not take into account the side chain. Now remember that the side chain will also participate in steric clash, right? So they will also participate in steric clash and would restrict some further rotation. So now what that leads to is that each amino acid then inherently gets a tendency to form helix, sheet, or turn. Okay, so this particular one is a chart which explains this phenomena that glutamic acid, for example, has a more propensity to form helix. Methionine has a more propensity to form helix, and so on. Okay, so you can if you put the side chains into the structure, so this tendency will start to come out. Okay, so that is that. So this plot here on the right side is the value of phi and psi for the amino acids except glycine in the enzyme pyruvate kinase. Okay, you can see that this predominantly falls into the two values where we found the minimum energy. Okay, glycines, they are not really what would I say? Glycines are not really that much of a, they do not fall into any category because glycines do not have a side chain, so they can take any conformation. Okay, so that explains the Ramachandran plot and how you can use it to predict the alpha helix, beta conformation, beta turn, as well as the tendency to form what the amino acid would be forming. That's that. So thank you for listening.